The final determinant of stroke volume and therefore cardiac output is contractility. Contractility is the intrinsic ability of the myocardial cells to develop force at any given preload and afterload. Notice that contractility and contractile force mean two different things. Contractile force is just a general term that refers to the strength of the contraction that the ventricle is making. And lots of things can affect contractile force, including preload and afterload. But contractility is different, and it's the intrinsic ability of the ventricle to make that contractile force. So contractility is an intrinsic property of the myocardial cells that determines the force generated by contraction independent of preload and afterload values. You can also think about contractility as the number of actin and myosin cross bridges that actually form, which is closely related to the intracellular calcium concentration, or how much calcium is released with every beat of the heart. The intracellular calcium concentration influences how many actin myosin cross bridges are actually made and determines the greatest contractile force the heart can make for any given preload and afterload. So the preload aligns the actin-myosin filaments, but there has to be calcium present for cross bridges to actually form and cycle. And the amount of calcium present is related to the contractility. If you increase contractility or the intracellular calcium concentration, that allows more cross bridges to form and cycle, so the stroke volume also increases. The strength of contraction in a cardiac muscle cell is dependent upon that intracellular calcium concentration. And in cardiac myocytes, both extracellular and intracellular calcium release is important to determine that final intracellular calcium concentration. Through the sympathetic nervous system, the cardiac myocyte can increase or decrease the intracellular concentration of calcium that develops during each heartbeat. It's possible then for the cardiac myocyte to change the intracellular calcium dynamics or kinetics. And since it's the intracellular calcium dynamics that generate the contractile force, they can change the contractility. If the level of intracellular calcium concentration per beat was increased, then the cardiac myocyte would be able to contract more forcefully and with a higher velocity because more actin-myosin cross bridges would be made, and the sarcomeres will be able to shorten even more than they used to for any given preload. So for any preload and afterload, if we increase the contractility, we're going to increase the stroke volume because there's an increased force of contraction just because of the increased amount of calcium released per beat. So contractility is heavily associated with the intracellular calcium dynamics. So there are a few factors that determine contractility, and the first and most obvious is that intracellular calcium dynamics. And the intracellular calcium concentration is affected by a few different things, including the sarcoplasmic reticular release of calcium, the influx of extracellular calcium across the plasma membrane, and the removal of calcium from the cytoplasm during relaxation. So if there's any change in intracellular calcium concentration, that directly affects the contractility. In this graph showing the intracellular calcium concentration over time, the black line shows the normal rise in intracellular calcium for the duration of one action potential. If the activity of the sympathetic nervous system was increased, or there were increases in circulating epinephrine or norepinephrine, that would cause an increase in the intracellular calcium concentration and therefore an increase in contractility, and that's what you see in the red line. So that increase in intracellular calcium concentration results in more actin-myosin cross bridges being formed and a greater force of contraction or increased contractility. And if calcium influx was inhibited, for example with a dihydropyridine inhibitor like in the blue line, this would lead to a decrease in the intracellular calcium influx during an action potential, and therefore a decrease in the number of actin-myosin cross bridges formed and less contractile force developed or decreased contractility. But there are also other determinants of contractility. For example, the activity of the myosin ATPase affects contractility. The myosin ATPase is the key enzyme responsible for actin-myosin cross-bridge cycling, and its activity is normally determined by genetic factors. However, it's possible to increase its activity through training, and an example of this is an Olympian like Michael Phelps. So increasing the myosin ATPase activity would increase contractility. Myosin ATPase activity and therefore contractility can also be decreased by certain disease states like heart failure and by aging. ATP levels also affect the contractility of the heart. So for example, when the heart is ischemic, that will lead to decreased ATP and ultimately decreases in contractility because there's no ATP available for the normal functioning of myosin. And finally, the number of functional sarcomeres can determine contractility. So a heart muscle can either hypertrophy or atrophy depending on its activity. So if a heart has more or less sarcomeres in it, that will directly affect contractility. So increasing contractility increases the stroke volume no matter what the preload is and no matter what the afterload is. Contractility is important because no matter what the preload or afterload are in a given situation, the cardiac muscle always has a way to increase its force of contraction. So if the preload is low or if the heart is pumping against a really high afterload, both of those things can cause a low stroke volume. But the force of contraction can still be increased by increasing the intracellular calcium concentration, for example, to try to get that stroke volume back up to physiological range. This is a way for cardiac muscle to increase the force of contraction no matter what is pumped into it and what it's pumping against. Now let's look at contractility on the pressure volume loop. So this point at the end of isovolumetric contraction is the point at which the pressure in the ventricle exceeds the pressure in the aorta, and so the aortic valve opens. Blood is ejected into the aorta until the length-tension relationship at this given active curve is reached. At this point, the cardiac myocytes have reached their maximum amount of force for that given starting length, and they can no longer exert force. The ventricle then begins to relax, and the heart resets to get ready for the next beat. So the contractility then is essentially measured by this active curve. And remember, at every point along this active curve, there's a maximum contractile force that can exist for a given preload. So if this line shifts up and to the left, there's an increase in contractility. And if it shifts down and to the right, that's a decrease in contractility. Since this active curve isn't always accessible, another way to estimate the contractility is by looking at the point at which the aortic valve shuts. That'll tell us the point where the myocytes can no longer shorten or they can no longer contract. So if it moves up and to the left, then we know we've had an increase in contractility because they can exert a greater pressure at a smaller length. Now let's look at how the loop changes with an increase in contractility due to, say, an increase in intracellular calcium concentration. So this blue pressure volume loop and the black active curve are considered a normal heartbeat. An increase in contractility would shift that active curve up and to the left. So let's go through the steps of the cardiac cycle with that increased contractility. First, we'll allow the ventricle to fill to its normal preload value. Then the ventricle will contract during the isovolumetric contraction until it reaches the pressure in the aorta. Here the aortic valve opens and the ventricle ejects blood into the aorta. And now, because of the extra actin-myosin crossbridges that are formed due to that increased intracellular calcium concentration, the ventricular myocytes can shorten further to a smaller length. And because of this increase in contractility, more blood is ejected from the heart. Following ejection, the aortic valve shuts, and because more blood has been ejected from the ventricle, the aortic valve closes at a smaller ventricular volume. After the aortic valve closes, isovolumetric relaxation begins, and then the cardiac cycle starts over. So the original stroke volume of the normal heartbeat is the width of this blue loop. And the new stroke volume of the heartbeat with increased contractility is the width of the red loop. The increase in contractility has resulted in an increase in stroke volume. So this red loop shows an increased contractility with the same starting preload as our normal heartbeat. Now let's look at what happens when the preload is less than normal, but there's that same increased intracellular calcium concentration and therefore increased contractility. First, we'll allow the ventricle to fill, but only to this smaller volume or smaller preload. Then there's isovolumetric contraction. The aortic valve opens and there's ejection. And because the contractility is increased, the ventricular myocytes can shorten further to a smaller length, generating more force before isovolumetric relaxation, and then the cycle restarts. So this is the stroke volume for this green loop, where we decrease the preload but increase the contractility. Under normal circumstances, decreasing preload would be expected to decrease stroke volume, and you'd have a more narrow loop compared to your normal beat. However, increasing contractility at that lower preload brought the stroke volume back up, and it's actually about the same stroke volume as in the normal beat. So remember, contractility is independent of preload. So increased contractility results in increased stroke volume regardless of the preload value.